I was sitting at my kitchen table this morning, just drinking coffee, watching my robot vacuum get stuck on a rug fringe for like the third time this week. And I had this realization, we are living through the absolute weirdest paradox in human history.
Which paradox is that? The one where we have all the human knowledge in our pockets, but, still argue about whether the Earth is flat.
No, well, yes, that one too. But I'm talking about the intelligence paradox.
Yeah.
I mean, think about it. We have AI right now, digital AI that can write a Shakespearean sonnet in seconds. It can pass the bar exam.
You can code a website from a napkin sketch.
Exactly. It's a genius, arguably, but if I ask that same genius to, say, walk into my kitchen, pick up a dirty shirt and put it in the hamper,
Oh, that's a complete catastrophe.
it's a total disaster. It trips, it knocks over my coffee, or just sort of freezes up and hums at me. Why is it that the things we think are hard, like calculus and chess, computers solved decades ago, but the things we think are easy, like folding laundry or clearing a table, are just mathematically excruciating for a machine?
It's the great irony of the 21st century, isn't it? We basically solved the mind before we solved the body. And that is exactly what we are unpacking today. We're looking at a stack of research that claims we are finally crossing that threshold. We're moving from disembodied intelligence to what they're calling physical AI.
Physical AI. It sounds simple, but the sources imply this is a massive leap. It's not just about putting ChatGPT inside a robot body, is it?
No, not at all. And that's a crucial distinction. Up until now, we've been dealing with what the researchers call disembodied AI. It lives on servers. It processes symbols, text, pixels. It's an open loop. You give it a prompt, it gives you an answer. There are no consequences.
Right.
Physical AI is different because it's instantiated.
Instantiated. That's a heavy word. What does that mean in practice?
It just means it has a body. It occupies physical space. And because it has a body, it has to operate in what's called a closed loop.
Okay, walk me through that. What's a closed loop for a robot?
Okay, think about when you pick up a glass of water. Your eyes see the glass, your brain tells your hand to move, your fingers grasp it. But here's the loop. Your skin feels the cold, your muscles feel the weight, and if that glass is slippery, your nerves instantly tell your brain, squeeze tighter. You are constantly perceiving the world, acting on it, and then perceiving how the world changed because of what you just did.
And you're doing all that in real time while, fighting gravity.
Exactly. You're negotiating with physics, thermodynamics, friction, momentum. A digital AI just has to worry about syntax. Physical AI has to worry about the fact that if it makes a calculation error, it breaks something real.
So the whole mission here, and the sources are very clear on this, is moving away from just simple automation. That robot arm in a factory that moves from point A to B, completely blind. If you move the car door, it just welds the empty air.
Right. That's just blind repetition. We are moving towards agency, towards machines that can actually look at the messy, unpredictable world and reason about how to achieve a goal within it.
So how do we give them that agency? Because looking at the research on World Foundation models, this seems to be the big breakthrough. We all get LLMs, large language models. They predict the next word. What does a World Foundation model predict?
It predicts the next physical event.
That sounds almost like precognition.
In a way, it kind of is. You're basically giving the robot an imagination. Think about it. When you walk through a crowded room, you're not doing complex trigonometry in your head. You're running a constant low-level simulation. If I step there, I'll bump that chair. If I squeeze through here, I'll fit. You're predicting the future state of reality based on your actions.
And that's what these World Foundation models do for the machine. They give it an internal simulator.
Exactly. The research highlights NVIDIA's Cosmos model as a prime example here. It doesn't just see a video feed as a series of changing pixels. It understands geometry, it understands semantics, and it understands time.
The semantics part is interesting. So that means it knows what things are, right? Not just, this is a gray blob, but this is a coffee cup.
Right. And it understands the properties of a coffee cup. A cup holds liquid, it's rigid. If I drop it, it's going to shatter. The Cosmos study gave this fascinating example with safety compliance. It could look at a video of a worker on a wind turbine. A normal camera just records pixels. Cosmos reasons. It asks, is that person wearing a harness? Is the harness actually clipped to the safety line?
So it's not just seeing, it's verifying reality against a set of rules or expectations.
It's counterfactual reasoning. It can simulate, okay, if that worker slips right now, what happens? And if the answer is they fall to their death, the AI flags a safety violation. It understands the physics of the fall before it ever happens.
That is a massive jump from just simple object detection. But then you have the Google approach with Gemini robotics. They're talking about VLA models,
Yeah.
vision language action.
And this is where it gets really interesting for the user experience. If you've ever seen someone try to program an industrial robot, it's a nightmare. It's just lines of code, coordinates, degrees of rotation. VLA models allow for open vocabulary instructions.
Meaning I can just talk to it, like I'm talking to you.
Precisely. The example in the source was just, place the smallest can in the lunchbox.
You know, to a human, that's such a throwaway sentence, but I was reading the breakdown of what that actually requires, and it's incredibly complex. Smallest is a relative concept. You have to see and compare all the cans. Lunchbox means identifying an object that might be open or closed, and place implies a gentle trajectory, not just, throwing it.
And the robot has to figure all of that out on the fly. The Google team showed this off with their Aloha platform. They had robots folding origami, packing lunches, playing card games. But the one that really impressed the engineers was adding snap peas to a salad with tongs.
Why that one? The snap pea thing sounds so trivial.
Well, if you ever use tongs, it's a lever. You lose all that fine tactile feedback. If you squeeze a snap pea too hard, you crush it. If you're too gentle, it slips out. For a robot to modulate that pressure based on visual cues alone, basically predicting the squishiness of the pea, that's a huge triumph of these feedback loops.
And the sources kept mentioning this concept of generalization. That's the holy grail here, isn't it?
It is. It means if you train a two-armed robot to fold a shirt, you can then transfer that knowledge to a humanoid robot or even a one-armed robot. The AI isn't memorizing the motor movements of one specific machine. It's learning the concept of folding. It learns the task, not just the trajectory.
Okay, so we have the brain, these World Foundation models, but a brain in a jar is useless. It needs to sense the world. And this is where I feel like we humans are a bit arrogant. We think vision is like the only way to see reality.
We are very biased towards our eyes.
Yeah.
But if you're a machine, the visible light spectrum is just this tiny, tiny slice of the data that's available. You have thermal imaging, LiDAR, radar, vibration sensors, audio.
But isn't that just a mess to process? I mean, a thermal map looks nothing like an audio waveform. They're completely different data formats. How do you even combine them?
That's the exact problem Archetype AI is solving with Newton. The researchers called it the Rosetta Stone of sensors.
I loved that analogy.
It's perfect, isn't it? Think about the actual Rosetta Stone. It let us translate Greek into hieroglyphics. There were different languages, but they held the same meaning. Newton takes all these different sensor languages, heat, sound, vibration, and it translates them into a single universal embedding space.
Universal embedding space? That sounds like some serious sci-fi jargon. Unpack that for me.
Imagine if every language on Earth, English, Japanese, Swahili, could be instantly converted into one single pure meaning. That's the embedding space. Doesn't matter if the data came from a microphone or a thermometer. Once it's in that space, the AI understands it as a single physical fact about the world.
So it creates this unified, multisensory picture of reality.
Exactly. And the coolest part is how we can interact with it. They use what they call semantic lenses. It lets you just ask questions to the data in plain English. You don't have to be a data scientist looking at vibration charts. You can just ask the system, is this motor about to fail?
And the AI looks at the heat spike. It hears a subtle grinding noise that a human ear would miss. It feels the vibration pattern change, and it says, yes, imminent failure in about 4 hours.
It makes the invisible visible. It's truly superhuman perception.
All right, so we have the brain, we have the senses, but here's the roadblock. The sources call it the robotics data gap. We train ChatGPT on the entire internet, trillions of words. But we don't have an internet of physical experiences, do we?
You don't. And getting that data is painful. I mean, really painful. Robots are slow. They break. If you want a robot to learn how to pour coffee by trial and error in the real world, you're going to have a very wet, very messy kitchen for about 1,000 years.
Not to mention the cost of the robot itself. One mistake and you've broken a $100,000 machine.
Exactly. So how do you get trillions of hours of data without waiting trillions of hours? You enter the matrix.
Simulation.
But not just video games. We're talking about high-fidelity, differentiable physics simulations.
Differentiable. That's a specific term the researchers used. What does that actually mean for the robot that's learning?
Okay, so in a normal video game, if a character hits a wall, they just stop. The game engine says collision. It doesn't really explain why. Differentiable physics is different. It provides the mathematical gradients. It tells the AI why it stopped and exactly how much it needs to adjust its force or angle to not hit the wall next time. It allows the AI to learn mathematically from every single mistake instantly.
So it's learning from the physics itself. And to keep the AI from getting too comfortable in there, they use something called domain randomization. I found this hilarious. It's like they're actively gaslighting the robot.
It is a bit cruel. Inside the simulation, they just constantly change the rules. They'll turn gravity up and down. They'll make the floor pure ice. Then suddenly it's sandpaper. They change the lighting to, like, disco strobes.
Why torture the poor thing?
For robustness. If a robot can learn to walk on simulated ice under a strobe light with double gravity, then walking on a normal carpet in a well-lit room is a piece of cake. It prevents the AI from just memorizing one specific environment. It forces it to learn how to truly adapt.
There were a couple of specific models mentioned here that help bridge this sim-to-real gap. One was the Genie Envisioner.
Right. Genie is a world simulator. It lets the robot dream, in a sense. It can generate millions of video rollouts of potential futures. What if I drop this? What if I slip on that? It learns from experiences it hasn't even had yet.
And then there's Pi Zero. This one seemed focused more on the quality of the movement.
Pi Zero tackles the jerkiness problem. You know how robots usually move? It's all stop, turn, extend, stop. It's very rigid. Pi Zero uses something called flow matching technology to smooth those movements out into fluid trajectories. The use cases they tested were things like bussing tables and doing the laundry.
The laundry again. It always comes back to laundry.
It's the ultimate benchmark. Cloth is a deformable object. It changes its shape every single time you touch it. It wrinkles, it bunches up. Trying to fold a fitted sheet requires a level of fluid adaptation that rigid, pre-programmed coding just can't handle. Pi Zero is making that movement look almost human.
So we've built the tech stack, we've got the brain, the senses, the training simulation. Now I want to zoom out. One of the papers gave this taxonomy, the 7 levels of physical AI. And I think this is really helpful to place where we are now and, where we're going.
It's a great framework. It really maps out the entire journey from, well, dumb machine to planetary intelligence.
Let's run through them. Level 1, reactive automation.
This is your 1980s car factory. A robot arm welds a door. If you move that door 3 inches to the left, the robot welds empty air. It's blind, deaf, and dumb. It's just following a script.
Level 2, adaptive assistance.
This is your Roomba. It has some sensors. It bumps into a wall and it turns around. It'll pause if a cat walks in front of it. It has basic awareness, but no real understanding. It knows obstacle, but it doesn't know cat.
Level 3, cognitive autonomy.
Now we're getting into the teenager phase. These systems actually model the world. Think of a Waymo or a Tesla FSD in a geofenced area. They plan routes, they handle traffic, they make decisions, but they can still get confused by weird edge cases, like a person in a chicken suit crossing the road.
Okay, level 4, full autonomy. This is where it starts to get a little sci-fi.
Level 4 is all about self-maintenance. These robots have a digital twin of themselves stored in their own memory. So if a gear starts grinding, the robot notices the sensor data doesn't match its perfect twin. It realizes, I am injured. And it can update its own code to compensate for the limp. It self-heals its own operation.
That is incredible utility, but also slightly unsettling. A machine that knows when it's hurt. Okay, level 5, collective intelligence.
Swarms. This is basically biology envy think ants or bees. Instead of one big, expensive robot, you have 100 small, cheap ones. If one drone finds a survivor in a forest fire, the entire swarm instantly knows that location. They share a brain. No central commander is needed.
Level 6, societal symbiosis.
This is the manners layer. A level 6 robot doesn't just know how to open a door. It knows when it should hold the door for you. It understands social cues, proxemics, personal space, and social norms. It's not just physically competent. It's socially competent.
And finally, level 7, planetary intelligence, the big one.
This is the nervous system for Earth. Satellites, ocean buoys, forest drones, all interconnected. They aren't just watching the climate anymore. They're actively managing it, balancing energy grids, tracking deforestation in real time, maybe even managing ocean acidity. It's AI at the scale of the entire biosphere.
That's a massive vision. From welding a car door to managing the global ecosystem. But let's bring it back to what's happening right now. The sources point to a few areas where this is already hitting the ground. Healthcare seems to be the immediate winner.
Absolutely. The STAR system mentioned in the research is a real standout. It performed an intestinal anastomosis, which is stitching 2 pieces of intestine back together.
Which is incredibly difficult because soft tissue is slippery, it moves, it's messy.
And the robot did it with more consistent suturing than expert human surgeons. That consistency really matters. It reduces leaks, it speeds up recovery, it's taking the human variability out of surgery.
But the text also mentioned something that surprised me. Empathy. We don't usually associate robots with empathy.
No, but in a hospital, presence really matters. They're designing robots that can navigate sterile corridors without feeling like some big industrial machine. They yield to patients in the hallway, they move smoothly. It's about fitting into a care environment without disrupting that human connection.
Another huge area is disaster response, specifically those snake robots.
I love these. If a building collapses, a dog can't get in. A human certainly can't. But a robot that moves like a snake, it can slither through the rubble, twist around rebar, and use thermal sensors to find body heat deep inside a pile of concrete.
It's taking the morphology, the body shape that biology already perfected, and just making it metallic. And then there's space. NASA's
The
astrobeam.
little flying cubes on the ISS, yeah, they're cute, but they represent a really critical problem, latency.
The time delay.
Right. If you have a robot on Mars, the signal takes 20 minutes to get there.
Yeah.
You can't just joystick it from Houston. If the robot starts slipping off a cliff, by the time you even see the video on Earth, that robot has been dead for 20 minutes.
So autonomy isn't a luxury in space, it's a survival requirement.
Exactly. Space robots must have level 3 or 4 agency. They have to be able to look at that cliff, realize it's dangerous, and stop, all on their own.
So pulling this all together, we've looked at the brains, the senses, the training in the matrix, the applications. If you had to summarize this entire shift for the listener, what is the headline?
The headline is that we are moving from programming to teaching. For 50 years, we treated computers like calculators. We gave them inputs and expected exact outputs. Now we're basically raising them. We're showing them the world, giving them senses, and letting them figure out the physics for themselves.
It feels like we are finally closing that loop between the digital mind and physical matter.
That's it, exactly. We are giving the algorithms hands.
And that leads to a thought I want to leave everyone with. We talked about sim-to-real. We are building these massive, complex digital universes just to train these minds. These digital twins live thousands of lifetimes in a single day, learning and evolving inside the simulation.
Faster than any human could ever hope to learn.
Exactly. So here's the question. As those simulations become more and more high fidelity, and the AI becomes more and more capable, what happens when the digital twin becomes smarter, more experienced, and more capable than the physical reality it was meant to copy? When the map becomes better than the territory, what happens to the territory?
That is a question we might have to answer a lot sooner than we think.
Something to mull over the next time you're struggling to fold a fitted sheet. Maybe soon you'll have a robot to do that for you. Thanks for diving in with us.
Always a pleasure.